Hello guys, in this video I would like to explain about multiple linear regression in Python. We already we already have done about simple linear regression in Python, and if you have not went through that video, if you did not watch that video, the link to that video is given in the description of this video. So you can go and you can see, you can watch the simple linear regression in Python, also simple linear regression, or if you are interested in OR, because if you don't know that simple case, it may be not easy for you to understand multiple linear regression in Python and OR. So in this video I would like to explain first the theory about behind multiple linear regression, and then the interpretation of the multiple linear regression. What is multiple linear regression, how it is different from simple linear regression. So you can see on the screen this equation, and if you remove all these equation and only keep this y is equal to beta naught plus beta 1 x1 plus epsilon and remove this section until here, then this is simple linear regression model, because that have only one response variable and one covariate in the error term. So if you increase the number of covariates, mean independent variable x1, x2, then this is multiple linear regression model. And there are, a lot of 3 dot 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 mean there are many covariates here. Not many, maybe 2, 3, whatever. It's depend on the model and the nature of your data, nature of how much independent variable you have. This is general form of the multiple linear regression model. So usually we use a least square method for estimation, and I will do this not now for simple linear regression analysis when I have my graphic tablet. So how we can estimate, and I will do is by for simple linear regression analysis I will do by both method, maximum likelihood method and by least square method, and then we will have a comparison that how much they are different, are they identical or different. So just to verify the two method as well to evaluate. So this means that this is a multiple linear regression model. This have more than two covariates, and this is epsilon. And epsilon is the influence of all those variables on the response variable which are not considered in the model here, like x1, x2 up to xn. And this is the influence of other variable which is not included in this model. The influence of other variable and the response variable y, which are not considered here in this equation. It is given that the information is given that this is a dependent or response variable. Beta naught is y-intercept. Intercept mean y-intercept mean if this all variable covariate have 0 input, still y has a value that is beta naught. If you draw this on the plane like this, suppose this, so y must have a value here somewhere here. If all these covariates has no contribution, so y has maybe here whatever is depend on the variable. So y, the value of y when all covariates have 0 contribution is the intercept. Like this is b naught in this case. Beta 1 is the slope coefficient of x1, beta 2 is the slope coefficient of x2, and so on. And I already explained epsilon, the error term or the random error. So now beta 1, we can explain beta 1. Beta 1 is the change in the response variable per unit change in the x1. Given that the input from other variable is constant, it means that the other variable or have no contribution. And you can say this is the expected change or the expected change in the response variable. Beta 1 is the expected change in the response variable given per unit change in x1. When you change x1 1 unit and the change you observe on y, that is called beta, holding the other variable, the input from the other variable constant. And similarly beta 2 you can interpret. I will interpret this in detail in some slides so that you can know that in detail that how this regression, multiple regression work, because the most important thing is the interpretation of the results. And again, as I said many times in my videos, that you cannot interpret the model, the results of the model or the outputs of the model unless you know the structure of the model, the theory behind the model, that how the model work. So this is, keep in mind, very important. You need to understand the model, how the model is structured, how the model work. Then you can explain what output that model has. So this is I explained this already, but you can see that slope parameter. Beta 1 indicate the change in y for a 1 unit increase in x1, assuming all other variable x1, x2 are held constant. Yes, so the other variable are held constant, x2 to xn. Then the 1 unit change in x will give you some change in y that is represented by beta 1. And this may be not increase, this may be decrease as well. Beta 2 is it indicate the change in y for 1 unit increase in x2, assuming that all other variable, remember x1 and x3, because x2 is here. So this is beta 2, mean that the change in the response variable given that 1 unit change in x2, assuming that all other variable are held constant. And similar interpretation for these. Now the magnitude and direction are very important in the regression analysis. Remember, if beta I is greater than 0, there is a positive relationship between xi and y. Yes, that's true. The trend is positive increase, there is an increase. As xi increase, y expected to increase. If beta I less than 0, there is a negative relationship between x, I and y, and this is, of course, if the sign of this is negative, this means that the variable, the dependent variable is decreasing as xi increase, y is expected to decrease. So there is an inverse relationship. When x increase, as a result, y decrease. Absolute value of beta indicate that the strength of the relationship. Now this is an example, and this may be very productive for the student of psychology, economics, and social sciences and business administration, etc. Let's suppose income is denoted. This is the regression model, the estimated model, not the estimated. If you put these values in this, the estimated model, and then the error term, the expected values are here, so the expected error term is 0, so this will be no longer exist in this model. Income is equal to beta naught plus beta 1 education plus beta 2 experience plus beta 3 age plus epsilon. This means that beta 1 is the effect, the impact of education on income. Beta 2 is the impact of experience on income. Beta 3 is the impact of age on income, mean that change in the income due to age is represented by beta 3, and so on. Beta 1 education, if beta 1 is equal to 2000, mean that for each additional year of education, the expected increase in income is $2,000, holding experience and age constant. As we explained earlier, these two will, when you hold these two constant, when you're interpreting beta 1, you need to hold these two constants. So this will show the impact of income, impact of education on income is represented by beta 1. Beta 2 experience, if beta 2 is equal to 1500, means that for each additional year, remember this is yearly data, so interpretation is in the year. Education, of course, we can do in a year, maybe some small courses also, but of course it is in the year in this case. It means that for each additional year of work experience, the expected increase in the income is $1,500, holding education and age constant. And beta 3 age is age. If beta 3 equal to minus 500, it means that for each additional year of age, the expected decrease in the income is $500, holding education and experience constant. So this is the beta 3 has negative sign. This means that when this variable is increasing, age is increasing, your income, expected income, is decreasing by $500 in a year, holding the other two variable constant. So this is all about theory and about the model structure and the interpretation. And then let's move to Python, that how this multiple linear regression work in Python. Okay, we will generate some synthetic data, but of course you can use your own data. I will recommend you use your own data, reading from CSV, online, or whatever file. So you need to run these all for this. Remember these are some for regression, and this is for R square and R root mean square error as well. So if you're not running this, the error, you cannot calculate root mean square error and R square. So this is some set seed, and now I generated this X data and then some coefficient and generate Y data, and there are 3 coefficients. So you can see the data of X and Y as well here. Let's suppose X. This is a single variable, and you can see it should be okay, not shown. You can see the direction. Okay, there is some command which you can use for head and tail, so you can see the data of that variable, that how much variable are there. So we have 3 coefficients, so there should be 3 variables. Okay, yes. So now you need to split the data into train, test. So this is X train, X test, Y train, Y test, and this will distribute this data, and test will be 30% and the training will be 70%. And I already explained this function, so I don't need to explain it again. You can go back to my videos and you can see this. Now you need to develop the model. So model is linear regression, and now model fit X train, Y train. Just train the model. Okay. So Y predict. Okay, I'm doing for testing as well. So I'm doing prediction. So now Y period is equal to model dot predict X test. So the prediction have been done, and now you can calculate root mean square error and R square as well of this model. So you can now print mean square error, that is 0.559 is less, and you can check R square, that is 0.9. It's very good performance of the model. Now you can visualize the results. The results of the test data and the predicted data for the test. You have already a test data which is actual data for Y, and then you have predicted data for the response variable. So you can compare those 2 variables and to see how they are close to each other. So this plot will give you that data. I'm plotting observed data here, Y test. So this is the original data, and then I'm plotting Y predict, which I predicted for the test. I just put, in this model, I just put x1, x2, x3 for the test duration, and then I predicted the data for Y and the coefficient. Of course, these are from training duration. So the predicted Y is now compared with the, I'm plotting the predicted values against the actual value and see how close it is predicted. Just plot it together to see. Yes, that's very good performance. You can see how much closely it is predicted, and you can see here it is mentioned observed data by blue color and predicted data by a red color. So you can see how closely it is predicted. And now you can use probability density function as well, because that will give you the distribution of both data, and you can see how close their distribution is. Just plot it. Y-test, this function will plot the density function of the Y-test, the original data, and this is the label is original data. So run this command. You can see this is for Y-test original data, and now Y-pred, the predicted data which we predicted on the basis of the X values for the test duration. Okay, this is also plotted. Now the title is density, so this will be mentioned on the top. Plot X label, that's value. Plot Y will label, that is density. And then plot legend, this will give you the legend, and plot show, this will give you the plot. Run all together and you will see the distribution. Both data set probability density function. Yeah, that's very close. Also in the extreme values, not only the mean value which is here, but also the extreme values of the data has also been predicted very well. Look in the extreme, lower extreme and the upper extreme. It's very good. Again, I will say original data is mentioned by blue color and predicted data is mentioned by red color. So you can see how close they approximated this data by your model. Now there are some assumptions of of the regression analysis. You need to test the more normality, and you also need, okay, the assumption are here. So now you can test the above evaluation was numerically both graphs, the original data, I mean the line plot, and the probability density function. You can evaluate this by numerically as well by just using Kolmogorov-Smirnov test, which we have already done. So if you are interested, the link to that video is also given in the description of this video. So you just need to import this, and then you need to apply KS test to sample. Remember to sample, because this is Y test and Y pred, and D will store the test statistic and P will store the P value from this function. Just run it. Now calculate this. The test statistic is very low, so the P value will be very high. 0.9999 is almost 1. So in the Kolmogorov-Smirnov test, null hypothesis is that both data belong to the same distribution. So we accept the null hypothesis, the p-value is very high, and we say that both data sets belong to the same distribution. So we have done verification, evaluation of the model graphically by using line plot, and then by using probability density function plots, and then numerical by using Kolmogorov-Smirnov test. So we have done very good evaluation of the model. Now you can test the assumption. So this assumption is Durbin-Wilson test, which says normally used for testing the autocorrelation function. I mean that the data is not independently distributed, and if the value of the D is close to 2, this means that there is no autocorrelation, and if it is higher than 2, I means near to 0 and near to 4, then this means that there is correlation, autocorrelation. The video is available, so if you want to see, you can go. The link is given in the description, and you can see that video as well, watch that video as well. Okay, but I have not calculated the residual, so the residual can be calculated here. Just right, RS, just name it RS Y underscore TAS minus Y underscore PRED. Okay, so residual is just the difference between the true and the predicted values. So this is the residual, because okay, and the function is residual, so just name it like the same. You can change it here as well, it's no problem. Residuals. Okay, now call this function, because this is used Now DW test, and the DW test is 2.33. So this is close to 2. So you can say that there is no autocorrelation and the data is independently and identically distributed. So this is the one assumption. The other assumption is normality. For normality, you know that I already explained that you need to test. There are 3 tests normally available. There may be more tests, not 3. I know about 3 tests: Anderson-Darling test, Shapiro-Wilk test, and York-Bera test. So you can use any of these tests to test the normality of the data. Okay, so you can apply on the residuals and import this function, because this will not work without test. You can try. If I have not called it, no, not working. This is the problem. So you need to call it. Yes, working now. It's funktioniert jetzt. And now you can print, because the test statistic and the p-value are stored here. Just run it. Yes, the test statistic is 0.989 and the p-value is 0.31. So this means that the null hypothesis in the Shapiro-Wilk test is the data is from normal distribution. And yes, we accept the null hypothesis looking at the p-value, and we say that the data is normal distributed. So you have done everything. You have done, you estimated the model, you evaluated the model graphically and numerically, and then you test the assumption. You have done everything. Now you can use this model for prediction. If you have the values for the predictors, the x variables, the explanatory variable, you can do prediction, because you have done all the things. So this is, I think, enough for today. What we have learned in this video, I'll summarize in the end. We have learned about the multiple linear regression model, and the assumptions, the structure of the model, the interpretation of the model, which is utmost important. And then we have learned that how this model can work in Python, how we can implement this model in Python. And okay, thank you very much, and see you in the next video. Ciao.